Good morning all. Today I am here to present on the topic Performance-Based Seismic Design. I am Karthi from the Department of Civil and Structural Engineering from DAS and Partners Engineering Consultancy. So let's begin. So what is PBSD? So it's a performance-based seismic design which is a problematic outcome-driven framework that explicitly links structural design decisions. It is used to quantifiable seismic performance metrics such as drift, loss, and downtime. It varies across the different multiple hazard levels. So, comparing to the general design, what is the difference between the general force-based design and performance-based design? So, as you can see in the table, force-based design is a single hazard level, but for performance-based design, we can go with multiple hazard levels. Similarly, it's a prescriptive R factor reductions. In force-based design, it is binary pass or fail, but in performance-based design, it is probabilistic performance design. Code compliance will be equal to safety, but in performance-based, quantified risk and loss estimation is the major criteria. So the core principle of the performance-based design will be the structure's expected behavior under realistic ground movements must satisfy the predefined performance objectives with acceptable criteria. So the seismic performance objectives are of different types. There is 4 categories mainly. It is operational OP, immediate occupancy IO, life safety LS, collapse prevention CP. So while discussing about the operational OP, it should be fully functional. Negligible structure or non-structural damage should be there, and IDR should be less than 0.2%. While coming to the immediate occupancy, it's a safe re-entry post-event mechanism. The minor cracking, no yielding, the value of IDR should be less than 0.5% to 1%. The structural integrity in this case is preserved. Life safety comes significant damage but no injuries or no collapse. Egress routes are intact and the IDR value should be between 1.5 to 2.5%, which means the repair feasible but it will be costly. Collapse prevention, it's near collapse, that's there will be major damage. The gravity system will be functional and the IDR value will be less than or equal to 4 to 5%, and the structure may be irreparable. So seismic hazard categorization. The probabilistic seismic hazard analysis, it integrates the contribution from all earthquake values, its sources, its magnitudes and distance to compute the annual probability of exceeding to a ground motion intensity level. And the design hazard levels are of different types. The SLU value is the service level earthquake, it should be 50%. The DBE, the design basis earthquake, it should be 10%, and the risk targeted MCE should be 2%. The structural modeling requirements while using a performance-based design method. The material should be non-linear. The concrete confined or unconfined models should be bilinear or Ramberg-Osgood steel. Then the FEMA 356 or ASC 41 hinges should be used, and the P delta effects should include leaning column, that is critical when theta is equal to P delta. The damping ratio, the Reynolds or model, the RC by steel value, avoiding artificial damping in NL analysis. Coming to the isolation or damping devices, bilinear or trilinear historic models should be used. While checking the histogram here, you can see that there will be different sorts of material requirements that is needed for the structural modeling. For example, plastic hinge models, system effects and devices, and material nonlinearity, that is the stress strain fiber sections. The modeling fidelity directly controls the reliability of demand predictions at each performance levels. There are mainly 3 analysis model in PBSD, that is nonlinear static pushover, nonlinear time history, incremental dynamic analysis. In the NSP, monotonically increasing lateral load profile is used. The capacity curve converted to ADRS format. The performance point is that the intersection with the demand spectrum or the target displacement coefficient method is used here. Similarly, in nonlinear time history, the suit of greater than or equal to 11 scale is used. The response quantitative averaged or envelope captures the rate effects, duration, sequence, dependency, etc. In IDA, the multiple NLTHAs at increasing IM levels produces IM EDP curves revealing softening, hardening and collapse seat. Now the acceptance criteria and the performance metrics that should be used while using a PBSD design. The parameters are mainly IDR RC frame, IDR steel MRF, IDR shear wall, residual drift, beam chord rotational. So you can see in the table there are different levels for IO, LS and CP. While analyzing the table, you can see that the beam chord rotation value for IO is 0.005, LS is 0.02 and CP value will be 0.03. And the governing standards that are used in the design will be ASC 4123, FEMA P58 and Eurocode 83. So how does this PB design work? The workflow will be the site hazard initially, the PSHA hazard curves, spectral charges will be analyzed, then the performance goal will be set. That will be IO, LS, CP linked to the hazard levels. Then the preliminary design comes into action, the system selection and member sizing. Then the non-linear model, the material is modeled, hinged according to the P delta values. Then the non-linear analysis is done with the pushover, NLTHA, IDA runs. So each iteration loop reduces the uncertainty and tightens the values margin between structural demand and capacity. Convergence is achieved when all EDP satisfies the acceptance criteria at all target hazard levels simultaneously. So these are the three different case studies that are used, where the PB design is used, which is the RC high-rise in Los Angeles, which is a 42-story RC core wall tower. The performance value was set as the LS at DBE, CP not reached until that MCR. Then the next example is the steel moment frame at Seattle. It's a 12-story SMRF SAC project benchmark where used the pushover plus IDA suit. Median collapse IDR is 10%, which is at 84 percentile, which is equal to 14%. And FEMA 350 acceptance criteria satisfied at 2/50 hazard. Then the last one is the base isolated hospital at Japan. It's a 8-story RC hospital on a hybrid isolation. The floor acceleration is reduced to 65% versus fixed base when the PB design was used. All these case studies benchmarked against the code compliance force design, and it shows that the PBSD consistently reveal performance gaps and enable to targeted cost-efficient improvements. So what are the advancements, challenges and future direction in this design category? The recent advancements are the self-centering and low-damage systems, supplemental damping, data-driven and ML-assisted PBSD and multi-hazard PBSD. The challenges and future direction in PB design will be the NLTHA suits for total buildings, for tall and all buildings. The hundreds of CPU hours, cloud HPC and reduced order models are grinding up. The code evolution, as we all know, the code are developing day by day and it is revising on every revisions. So the ASC 728 expected to expand the PBSD provisions. Risk-informed performance criteria is also included in this version of ACE code. The model uncertainty. Epistemic and ulterior uncertainties in material models, hinge parameters and ground motion selection remain still significant. So these are the uncertainties and the future direction in PBSD. Thank you.